Today's class, we are going to see about thermoelectric diagrams. We all know that thermocouple is made from two metals A and B. The difference of temperature of the junctions is T. The thermo EMF is given by the equation E is equal to AT plus BT squared. A graph drawn between T and the thermo EMF is a parabola. If we differentiate this equation, dE by dt is equal to A plus 2bt, where dE by dt is called as the thermoelectric power. A graph drawn between thermoelectric power and the difference of temperature is a straight line. This graph is called as a thermoelectric power line or a thermoelectric diagram. We all know that the Thomson coefficient of lead is 0. So generally, thermoelectric lines are drawn with lead as one of the metal of the thermocouple. The thermoelectric line of a copper-lead couple, this couple has a positive slope, while that of iron and lead has a negative slope. Uses of thermoelectric diagrams. First, we are going to determine the total EMF. Let Mn represents the thermoelectric power line of a metal like copper coupled with lead. So Mn has a positive slope. Let A and B be 2 points corresponding to a temperatures T1 and T2 along this temperature axis. Now consider the small strip of A, B, C, D of thickness dt with junctions maintained at a temperatures T, and this is T plus dt. The EMF developed when the two junctions of this thermocouple differ by a temperature dt is dE is equal to dt into dE by dt, that is nothing but the area A, B, D, C. The total EMF developed when the junction of the couple are at a temperatures T1 and that is temperatures at T1 and T2 is, we have to integrate this between the limits T2 and T1 dt into dE by dt. Therefore, this area A, B, D, C. Next, determination of the Peltier EMF. Let pi1, pi2 be the Peltier coefficients for the junctions of the couple at a temperatures T1 and T2 respectively. The Peltier coefficient at the hot junction T2 is given by pi1 is equal to T1 into dE by d2 at a temperatures T2. That is the OB into BD. Therefore, the area OBDF, OBDF. Similarly, the Peltier coefficients at the junction T1 is pi1. Therefore, T2 into dE by dt at a temperatures T1. That is OA into AC. Therefore, the area OACE, where pi1 and pi2 are given as the Peltier EMFs at a temperatures T1 and T2 respectively. Therefore, the Peltier EMF between the temperatures T1 and T2 is given by pi2 minus pi1, that is the area OB, the area OBDF minus the area OACE, this area, minus this area. Therefore, remaining is the area ABDF ECA. This is the Peltier EMF. Next we have to determine the Thomson EMF. If the total EMF developed in a thermocouple between the temperatures T1 and T2 is given as ES is equal to pi 2 minus pi 1 plus integral sigma A minus sigma B into dt. This we all know that. Here sigma A and sigma B represents the Thomson coefficients of the two metals constituting the thermocouple. If the metal A is a copper and B is lead, we all know that the Thomson coefficient for lead is 0. Therefore, sigma B is equal to 0. Substitute in this equation, ES is equal to pi 2 minus pi 1 sigma A dt. Therefore, keeping this here, if we bring this minus of pi 2 minus pi 1 minus EF. Thus, the magnitude of the Thomson EMF is given by ETH pi 2 minus pi 1 is equal to area A, B, D, F, E, C, A. This area minus the area A, B, D, C. This area minus this area. Therefore, the remaining area is C, D, F, C. C, D, F, E, the remaining area. This area is the remaining area. Next one is thermo EMF in a general couple, that is the neutral temperature and the temperature of EMF inversion. In practice, we know that the thermocouple may consist of any two metals. One of them need not be always lead. Figure shows the thermoelectric power lines of copper and lead with respect to lead. Copper, this one is copper, this one is iron with respect to lead. Let T1, T2 be the temperature of the T1 and T2 be the temperature of the cold junction and the hot junctions corresponding to the points P and Q. EMF of the copper lead thermocouple is area P Q B1 A1. This is copper. Therefore, EMF of iron lead thermocouple, we will take this. This is the area P Q T1 C1. Therefore, the EMF of copper iron thermocouple is, we have to subtract these two areas, that is area P Q D1 C1. This area minus area P Q this area. Remaining is the area A1, B1, D1, C1. This area, remaining area is this. The EMF increases as the temperature of the hot junction is raised and become maximum at the temperature Tn, where the two thermoelectric power lines intersect. At this point. This temperature Tn is called as the temperature of that is the neutral temperature. As the thermo EMF becomes maximum at the neutral temperature, dE by dt is equal to 0. Suppose the temperature of the junctions T1 and T2 for copper iron thermocouple are such that the neutral temperatures Tn lies between this T1 and T2, then the thermo EMF will be represented by the difference of the area dE by dt, that is A1 N C1 and B1 D1 N, because these areas representing this area like this opposing EMF. In particular case, when Tn is equal to T1 plus T2 by 2, these areas are equal and the resultant EMF is 0. Therefore, the directions are opposite. In this case, T2 is the temperature of inversion of copper ion thermocouple. Thank you.